Welcome to 1514 FTI-MTM on digital signal processing. This is the first course in a series of courses on DSP. And before taking off with the first lecture, I'd like to tell you something more about the reason why we are studying digital signal processing. Let's start by taking a short look back in history. Since the late 70s of last century, digital electronics has become mainstream. Analog electronics, on the other hand, has become almost obsolete. And I will tell you more about that shift in technology from analog to digital during the first lecture. Now, should we look down on analog electronics as if it were inferior? No. State-of-the-art analog electronic circuits will be part of our everyday lives forever. The reasons for that are manifold. The most obvious one, and that's one that suffices for now, is our world is analog. Still, you won't find a lot of pure analog devices remaining in our daily lives, and there are good reasons for that, and we will touch upon them during the first lecture. Now, the result of this shift from analog to digital is that the electronics engineering curriculum contains courses on digital electronics, computer architecture, embedded systems, and so on. Courses that did not exist in the 70s of last century. Today, you are faced with another of these digital courses, 1514 FTI-MTM on digital signal processing. Now, what's so special about signals that we need to study them separately? You do know all there is to know about digital gates, flip-flops, state machines, ALUs, multipliers, memory, and so on. Right? So, why digital signal processing? Well, when discretizing signals, strange things happen. And understanding these peculiarities is key to being able to process those signals. During the remainder of this video, I'd like to illustrate some of these strange effects to you. Why? Well, to motivate you to persevere in studying one of the more difficult subjects you met so far, DSP. I selected a small music fragment for the examples that follow. It is the intro of an instrumental rock number by Jason Shaw. Let's start by listening to it. Let's take a look at this audio fragment from the perspective of signal processing. It is a stereo fragment, and that means it's normally reproduced using two speakers. The fragment also has been recorded in a studio using two microphones, and it has just been played back through your speakers or headphones. Below is a graph of the electrical signals that have been recorded and are being sent to those speakers. One for the left channel and one for the right channel. These waveforms are very complex. Let's zoom in on them. We'll focus on the left channel. The signal, when zoomed in, still seems rather complex. So let's zoom in on it again. Now we start to recognize more simple waveforms, as you probably would have expected. Any signal can be seen as a sum of sine waves. We have seen that in the mathematics courses. And this signal starts to be sine wave-like, don't you think? For reasons that we will find out in the first lecture, these are not signals in the way we normally treat them nowadays. The signals depicted here are continuous time and value signals. We call them analog. In a modern signal processing unit, we will deal with discretized versions of these signals, the so-called digital signals. The setup therefore will look a bit different. Instead of using analog equipment to record and reproduce the analog signals, we will discretize the signals coming from the microphones using analog to digital converters, and then store them digitally. When playing the recorded sound again, we will reconstruct the original analog signals using digital to analog converters. Let's focus on the role of the ADC. It takes samples from the original signal at regular time instances and sends the actual signal value of that instant as a number to the digital recording system. This has been indicated on the bottom graph. Every one of those blue dots is such a single sample, and we took 1,380 samples per second. As engineers, we say the signal has been sampled at a rate of 1.38 kHz. Now, let's hear what the result is of this sampling process by listening to how it is reproduced through your speakers by the digital to analog converters. It sounds a bit dull, doesn't it? Can you explain? Pause the video now and take some time to try and come up with an explanation. Pause now. The video will restart in 5, 4, 3, 2, 1, 0. That was an obvious one, wasn't it? The sampling rate used wasn't high enough to capture all the high-frequency sounds, and these high-frequency sounds are what makes the audio sample crisp and clear. So, let's increase the sampling rate. First, we zoom in a little bit more. If we now sample the signal at a sampling rate of 44.1 kHz, we obtain the result down below. I have the impression that the sample signal is a good representation of the original signal, don't you think? Now, let's check what the result is by listening to how it is reproduced through your speakers by the digital to analog converters. Nice, right? Did you hear a difference with respect to the original fragment? Probably not. There's even more. What you just heard is exactly the same as the fragment you heard at the beginning of our experiments. When discussing Fourier transformation, we will prove that it is exactly the same. Not 99%, not 99.99%, but the full 100%. The analog signal coming out of the speakers is exactly the original waveform you see here on top. If you think about that, frankly speaking, that's baffling. By sampling, we have thrown away all the information in between the sample points. Yet, our digital to analog converters seem to be capable of perfectly predicting what was in between the sampling points. Please take some time after this video to think about that. Let's return once more to sampling the fragment at a lower rate, and let's reconsider sampling it at 1.38 kHz. Actually, this means sampling at a rate which is 32 times lower. In fact, this corresponds to keeping one sample and then throwing 31 away, keeping one sample, throwing 31 away, keeping one sample, throwing 31 away, and so on. We call this decimation by a factor of 32. Doing this should yield the music fragment we listened to before, shouldn't it? Let's check. This is how the result sounds. This is even more mind-boggling. I would have expected to lose detail in the music fragment, sure, by throwing away a lot of samples, but apparently there's new frequency content that has been added. Did you hear the strange resonance of the drums? The extra distortion when the guitar was playing? Well, this is due to a phenomenon called frequency aliasing, and it is inherent to the sampling process. It didn't show up in the fragment that was sampled before at 1.38 kHz, because I took precautions to prevent it from happening. Aliasing. It is just one of the effects that we will have to study in this course, in order to be able to prevent it from happening. Okay, in the past few minutes we've seen a number of examples to illustrate that strange things happen when we treat signals in discretized time. And we didn't even mention the strange things that happen when we start discretizing the values of those signals. So there's much more to come. To understand these effects, we need some mathematical analysis tools, the so-called signal transformations. These transformations will be your toolbox to combine the nuts and bolts of DSP into working systems. And to this end, you will need to tap into your mathematical knowledge base. And I hope that you will be pleased to find out that there is a very good reason why you studied maths during the previous years. Mathematics is a key foundation to understand digital signal processing. I wish you a fantastic journey in the world of DSP, and I look forward to meeting you in the first lecture. Thanks for watching.
you.